Hello and welcome to this presentation on an evaluation of serverless data processing frameworks presented at the 6th International Workshop on Serverless Computing. The work was authored by Jörn Kuhnkamp, Richard Gierke and me, Sebastian Werner. We are all from the Information Systems Engineering Chair at TU Berlin. We were motivated by this work from two facts. Well, as you all probably know, serverless is a new cloud computing execution model that offers auto-scaling and a pay-as-you-go cost model. These two things are very attractive for bursty workloads such as ad hoc data processing or exploratory data analysis. Because of that, researchers and industry professionals have started to create frameworks to use serverless computing solutions, usually fast-based solutions and fully managed storage solutions, to create processing pipelines. However, while these frameworks already exist, it's hard to compare them right now. So we asked the research questions: how can data analysts assess the quality of serverless-based frameworks for ad hoc data processing? In the paper, we offer three contributions: a structured overview of existing serverless data processing frameworks, an analysis of the architecture decisions in these frameworks, and an experimental comparison of publicly available serverless data processing frameworks, and Apache Spark running on AWS Elastic MapReduce. We started with a multivocal literature review, where we had basically two main questions. One, what serverless data processing tools exist in research and industry? And two, what use cases and purposes are these tools used for? We started with all the typical libraries and also some internal libraries where we collected blog posts and other interesting things regarding serverless. And from that, using the queries, we extracted a total of 245 publications. Using selection criteria and so on, we got it down to 76 that we actually read and evaluated if these works presented frameworks and platforms used for data processing. Of these frameworks, we identified 18 candidates that we wanted to look into more closely and identified a total of 11 frameworks that were one framework, so they allow you to describe an analytics work abstractly, and two, that allow general purpose definitions, so not only for like video encoding, but for all kinds of computation. Our results also showed for purposes that they were mostly designed for batch data analytics, and mostly between 2018 and 2019 these works were published. From the architecture point of view, we also noticed a few things. So first of all of these systems use an external driver system to coordinate workload and monitor them. These drivers, however, can be located at different points. Either they're remote, so on your laptop, so we have a command line tool usually that initiates the job, starts the functions, invokes them, calls either the storage service or waits for the results of the function service, and then invokes the next stage and so on. Or there are co-located solutions where a platform is deployed next to the function as a service offering, usually a VM, and in there the driver program needs to run. Then there's usually some sort of network communication between functions and driver involved. And we also have mixed solutions where you have a remote system that will deploy functions that then start other functions or monitor other functions and so on. We also noticed that at least 60% of the frameworks we discovered use an object store to actually facilitate intermediate data storage. So between stages, you have to store data somewhere because it cannot reside in the function, right? Two used queue as well for intermediate storage and also for invoking or informing intermediate stages of results. Then there's also two that use key value stores instead, so something like Redis. And there were also some others that use the driver directly. So if they're co-located, you can use the disk on the driver or the network communication on the driver to actually do some of the intermediate storage and communication as well. Most notably, on the other thing we noticed was that most of them target the AWS platform at the moment. There was only one exception, which was IBM Pyron, which targets the IBM cloud platform. But there are no frameworks that we could find for Google Cloud and Microsoft Azure at the moment. So these were the initial frameworks we discovered in our search. As you can see, 55% only of them had a source code available. 66% of them use a MapReduce programming model, so something that's pretty familiar to a data analyst who has done distributed computing before. And 18%, so two of them actually used an abstract programming model like Apache Spark. When we done the initial search for the paper, these were all the frameworks we found. However, in a later stage, we did a validation of our study and actually discovered two more frameworks. So the actual number of systems that we could have evaluated, a few more, with at least 63% of them having source code available. Anyway, for this paper, we evaluated 3 of these frameworks. We could have evaluated 4, but these 3 were all deployed on AWS and represented different implementation styles which we were interested in. So we evaluated Quable's Spark on Lambda implementation, the Coral framework, and the Pyron framework, the oldest one that we know of. All using AWS Lambda and S3. We also used an Apache Spark running on AWS MapReduce as a baseline. All of them could access the input data from S3, and we used a computer at Berlin to actually coordinate everything. We selected for our evaluation comparison the TPCH benchmark, which is a data warehousing benchmark. It defines data sets and a bunch of queries to evaluate these systems. We specifically selected 2 of these queries, Q1 and 6. One is a query that uses one group by, so you have at least 2 processing stages in map and reduce, where data has to be shuffled around. And Q6, which is a single map filtering stage, if you implement it, which we are also interested in just to see the difference between these 2 queries to get the first impression of how these frameworks look like. So the process, as you can see, also was quite simple. We first generated and uploaded the data to an S3 bucket. For this experiment, we selected 3 gigabytes at 300 megabyte chunks. Then we implemented the queries for the different frameworks. For Spark and Quabble, we could use the Spark SQL library, so we didn't have to do any implementation really. We just took the TPCH query and put it in there. For Coral and Pyron, we actually did have to implement them in MapReduce, and that's also why we chose these 2 queries. They're quite simple to implement, and because TPCH is an already established benchmark, there are also some reference implementations for MapReduce jobs out there, which we relied upon. So then we needed to deploy the infrastructure. So here there's a slight difference between the different frameworks. Some, like Pyron and Coral, allow you to deploy all or part of it using their tooling or scripts, while Coral and Apache Spark, you basically have to do some more legwork. Especially for Coral, you have to do a lot of manual deployments. Where possible, we select the same amount of memory and use the same driver and so on to ensure that's all the same kind of baseline. And then we ran the benchmark for each query separately 3 times with 15 minutes or more pause in between to see how these systems would perform on cold data. So for the results, all 3 serverless frameworks performed better than our baseline at about 60 seconds per query. Coral was the fastest for the embarrassingly parallel query 6 at 23 seconds. Quabble, interestingly, was quite expensive due to a high amount of read requests for each query, and also for the need of a quite big VM to manage everything. But overall, Coral and Pyron are quite suited for these ad hoc data processing tasks. They're quite cheap at 10 cents for an hour of queries, and Coral can perform 140 queries of type 6 and 50 for type 1. So they're quite usable for ad hoc data processing. Looking into the majority and developer experience for these frameworks, first thing you notice is that all 3 serverless frameworks are still very young, few commits, and not on active development right now. So the latest commit is 2019 at Coral. Quabble, latest commit is 2017. On the other hand, Spark, right, entire active development, lots of commits. So you expect some differences in the developer experience here. For Coral, we could see that it was quite difficult to actually deploy this whole system because it's not that well documented. We actually had to look at some forks of the projects to see how other people who keep developing it did it, and that helped, but it took a lot of time basically figuring out networking and issues like that. Coral and Pyron, on the other hand, are quite straightforward. So the tools offer deployment as well. You just have to configure everything. So you have to figure out what the configuration parameters actually do. But overall, it was simple enough. Implementation time was easy for all of them. And as you can see, for Spark, development time and implementation time are quite quick, right? If you're using EMR, you hit a button and 11, 12 minutes later, the cluster is running and doing your job. Then you have just to wait for the job to finish. So it's quite easy. In conclusion, we can see that only a few frameworks are publicly available to be evaluated. AWS is the data processing infrastructure of choice, but you can also see that serverless data processing is well suited for these ad hoc data queries. You don't have to wait for a cluster to boot up, and you don't have to wait for resources to be ready. You just hit a button and it will start the processing, and about 70 seconds later you have a result. In our case, it's quite nice. For future work, we plan to actually extend this experiment for all available frameworks. We here presented a method to do this comparison using the TPCH benchmark, and we're going to do this forward with all other existing frameworks. But we also wanted to look into more specifics like driver implementation and intermediate storage, how these things differ. And we currently have a bachelor's thesis going that actually takes the results of the paper and tries to extend it, look into file size differences and so on to see if there are any effects that you can measure. Thanks for your attention. If you're interested in the paper, I put a link up into the corner. And if you have any questions, feel free to reach out to any of the authors. And if you're interested in serverless features in general, just check out our chair's website or the project website that I'm currently working on. Thank you very much.